And we've tried to get this manipulator to draw, say a circle, something like this. Where this was our trajectory. And what we did here was we said this trajectory is something like this. The x is r cosine theta, y is r sine theta. And so the manipulator has to draw this trajectory. And what we did here was we have 2 degrees of freedom here, theta 1 and theta 2. We solved for theta 1, theta 2, and then the manipulator drew the trajectory. But in that particular, so theta 1, theta 2 based on IK, inverse kinematics. The issue with this was that when we did this, we assumed that the manipulator is drawing this curve in a static fashion. Okay, there is no time appearing in this theta 1 and theta 2. Okay, this was a static problem. Every time we wanted the end effector to be at a certain location, which was x and y, which is given by that equation of a circle. We solve for theta 1, theta 2, and then we just went, we solved this problem each and every point of that trajectory, and that's how we got the circle. But in the real world, you care about how you go from one point to another point. And so there is this component, space, the temporal component, which is important, was missing in this whole problem. So this example looked at spatial component or spatial trajectory, which is just the x and y, but it ignored the temporal trajectory. And if you want to represent the temporal trajectory, it would be, this would be x as a function of time, y as a function of time. And why is time important is because if I tell you to draw the circle in 1 second versus 2 seconds versus 5 seconds versus 10 seconds, you're going to have different effects based on how you program the robot. So it can do this task very slowly, no problem. But if you make it draw this circle very quickly, very fast, in like 0.1 second, it may not be even possible for the manipulator to draw it. And one of the reasons why it's not possible is you could have limits on the motors. The motors are not powerful. You could have a very heavy arm, so it cannot move fast enough, and so on. So considering the trajectory is important, and that's what is going to be the focus of today's talk. Okay, so we're going to look at, oh my God, we're going to look at the temporal component of the trajectory, how to generate that. Dynamic trajectories. That would be x as a function of time, y as a function of time. It could also be theta as a function of time, theta 1 as a function of time, theta 2 for the function of time, and so on. Okay, so we'll start with a simple problem, and then we'll just extend it to a complex one. So what I mean by the simplest problem is the simplest thing you can think about is if you look at the joint angle. Okay, so Q is the joint angle, and T is the time. You want to go from point A to point B. Okay, so Q0, QF are the initial and final positions of the manipulator. And then if you want to go from point A to point B, there are many ways to do it. You could go like this. You could just take a wild detour and come back. But probably the simplest thing to do and the most reasonable thing to do here is to just choose a straight line, right? That's the fastest way to get there. Straight line. And then when you given this endpoints, you also told in how many minutes, seconds you want to go from point A to point B. So our goal here is to see how to connect Q0 to QF with a straight line. Okay, that is, we are trying to find a function of time for that joint such that we go in a straight line. Now, this is probably very simple, but I'll sort of derive this, and then we'll rationalize why this is not a good idea to join it by a straight line, and why we want to do more complex things. So let's start with this and then move on. Okay, so here we are trying to connect it to the straight lines. I'll redraw this figure. Q of t, Q0, QF, T0, TF, and then of course a straight line. Okay, so let's try to compute Q of t. Now, it's clear that if Q of t is a straight line, then the equation of a straight line is simply a0 plus a1t. Right, that's the equation of a straight line. Okay, a0, a1 are unknown constants. Okay, so if you want to compute those constants, you need two conditions on those constants, and we actually have those two conditions. It's basically Q0, Q equals Q0 at t equals t0. So we can say that Q0 equals a0 plus a1 t0. I just substituted the value of Q at t equals t0. Similarly, Q equals QF at t equals tf. So we have QF equals a0 plus a1 tf. So what I'll do is I'll basically rewrite these equations in a matrix form, because then it's very easy to invert them with the tools we have at our disposal. So this can be written as follows. The right hand side is 1 t0 1 tf. The unknowns are a0 a1, and the right hand side is q0 qf. Right, I just rewrote the equations in a matrix form where this thing here, if you want, you can call that a. This is an unknown, let's call that small a, and this here is b, right? So this is an unknown. A is known because in a problem you'll be given what t0 and tf is, and you'll be given what q0 qf is. So in order to solve for a0 and a1, I just need to invert the capital A matrix. So let's just do that. So if you invert this, what you get is the following. You get QF, Q0 TF minus QF T0 divided by TF minus T0. That's the first row. And then we have QF minus Q0 divided by TF minus T0. So that would be A0, A1. And hence, if you try to write the expression for Q of t, this is our what we were after. What is the Q such that the trajectory is linear in time? That would be A0, which I will now substitute from the formula we derived. Q0 TF minus QF T0 divided by TF minus T0. That's A0 plus A1 times t. Right, this is A0, this is A1. Okay, very straightforward. There's nothing strange about this. It's very straightforward. If you can compute the inverse, you can do this. Now, one thing of interest is, what about Q dot? Q dot of t is the velocity. If you want to find Q dot, you just take the derivative of this expression, and you can see that the term on the left side, A0, first term, is a constant, so it will be 0. So all you'll be left with is QF minus Q0 divided by TF minus T0. So you can see that this is a constant. Okay, let's look at the consequence of getting this particular trajectory. We saw that the position Q as a function of t is simply a constant. Q0, QF. Okay, so the manipulator, the joint, is at this position, and then it can just simply go there in a straight line, all good. But if you look at the velocity, so Q dot of t is a function of time. Initially, the system would have, let me just put some coordinates here. Let's say T0 and TF. Same thing here, T0 and TF. So what's going to happen is, initially, since I'm beginning the motion, the velocity is going to be 0. And then you can see that the velocity is constant in for the whole maneuvers, which means that now the velocity is going to be a constant value. And then after TF, it again has to go to 0. Right? Because it has to come to a stop. If it's not 0, then the manipulator will fly away in different position. So we see that there is a discontinuity in the way the velocity is achieved. Okay, so this is, there is a jump in the velocity. So it goes from 0 to some non-zero value. And the issue with this jump in the velocity is that on paper that's fine, but if you're actually putting a motor and getting the motor to go from 0 speed to some high speed, then it could actually damage the motor. So this could damage the motor. So this is not what we want. We don't want our motor to be damaged. Now, it'll probably not be damaged in the first time you do this, but if you do this for like hundreds and thousands of times, then you clearly will damage the motor. So what people do is, well, let's fix this. Let's not only worry about the position, but let's also worry about the velocity. So the fix is as follows. So what we do is, we do specify the initial position. Let's call that T0, EF. But we also say that the velocity at the start should be 0, and velocity at the end should be 0. So this ensures the velocity does not change abruptly. Okay. So these are 4 conditions. So if you want to find an equation which satisfies all the 4 conditions, you can no longer do with a linear equation, because a linear equation has 2 constants, but we want to ensure that the equation we come about will be able to satisfy all those 4 conditions. So next we go from a linear equation to we can start assuming a third order equation. So we assume Q of t is a0 plus a1t plus a2t square plus a3t cube. So third order equation, 4 constants, which can be used to solve for the 4 conditions. So 4 equations comes from here, 4 unknowns comes here, and so we'll solve for those 4 unknowns. So these are 4 constants. So the way we'll solve for those 4 constants is the 4 conditions. So we'll also specify what Q dot is. We just differentiate that first expression. We have a1 plus 2a2t plus 3a3t square. And so we have the following 4 conditions. Q0 is a0 plus a1 t0 plus a2 t0 square plus a3 t0 cube. Okay, I just substituted the value of Q at Q0. Then we have QF equals a0 plus a1 tf plus a2 tf square plus a3 tf cube. But we're not done yet. We also have these 2 conditions. So we'll put those. So now we need to look at the derivative. So Q dot at time t equals 0 is 0 equals a0 plus a1 t0 plus, sorry, my bad. I should take the second expression. a1 plus 2a2 t0 plus 3a3 t0 cube, sorry, square. And then we have Q dot tf, which is the velocity at the end time is 0, is a1 plus 2a2 tf plus 3a3 tf square. Yeah.
Did we make it so that there's 4 constants because we now have 4 parameters?
That's right.
Okay.
We have 4 constants because there are 4 conditions, not parameters.
Okay.
Yeah. So these are the 4 equations. But there are 4 unknowns or 4 constants. Okay, a0, a1, a2, a3. And so we can solve for those by doing the same thing we did before. We'll set up a matrix equation for this. That equation will look something like this. I'm going to move the right-hand side to the left so it's easier to see. So it'll be 1 t0, t0 square, t0 cube, 1 tf, tf square, tf cube, 0, 1, twice t0, 3 times t0 square, 0, 1, twice tf, 3 times tf square, then a0, a1, a2, a3. And the right hand side we have q0, qf, 0 and 0. Okay, so clearly if you want to find the constants, you need to invert this matrix. Everything here is known. This is unknown. This is, by the way, also known. The whole times are specified in a problem. So you need to solve for a0, a1, a2, a3. You need to invert this big 4 by 4 matrix. 1 t0, t0 square, t0 cube, 1 tf, tf square, tf cube, 0, 1, twice. I'm just rewriting that same equation down, but just going to invert it. Square, 0, 1, twice tf, 3 times tf square, So invert this times Q0, QF, 0 and 0. Okay, so I'll show you code which does this. There's no point in trying to do this by hand. Okay, so this gives me Q of t, and then I can, of course, compute Q dot t. Okay, and I'll show you code. SymPy code in just a bit. But what is the result of this is that if you look at Q as a function of time, okay, earlier remember when we wanted to connect point Q0 and QF, QF Q0, we actually drew a straight line, and that was because the velocity was constant. But with this kind of an approach where the velocity is also important, we'll see that the curve will look something like this. Such that if you draw this, if you draw the tangent at Q0 and the tangent at QF, that's the slope of the line at Q0 and QF, the slope is actually 0. Okay, so it's not a straight line, but it slightly curves in, curves the slight curve. Of course, that curve is a third order polynomial like we've seen. And then if you now look at Q dot as a function of time, it actually is something like this, like a hump. Okay, so it's indeed 0 at t0 and 0 at tf, but there's a hump. So the velocity sort of goes to maximum midway, and then it goes back to 0. Okay, so you think that, well, problem solved. We had a problem with the straight line. The velocity was discontinuous. We solved it by doing this trick where we assumed a third. We created two more conditions, sort of created a third order polynomial, got the trajectory. There's no issue of discontinuity. However, if you look at Q double dot of t, okay, which by the way I've not written down here because that equation is kind of complex to solve, you will see that the curve will look something like this. So 0, 0 here at the start and end, but there is a discontinuity here. In acceleration. It's not only here, it's also here. So the acceleration will be 0, but it will suddenly change to some positive value because it's the manipulator is moving. Then it'll go linearly down. There'll be a point where it's 0, but then again, when you want to stop, it'll again go from some negative value to 0. And that is actually bad for the motors. Bad for motors. Okay, so that's not going to help because motors are driven by torque. Torque is proportional to acceleration. So how do we avoid this? How will you avoid acceleration discontinuity? You could just extend the idea which I just told you, which is you had 4 conditions, 2 being for velocity, 2 being for position. You could have 6 conditions. So to avoid this, add two more conditions. So those would be q of t0 is q0. We've had that before. Q of tf is qf. Q dot of t0 is 0. We had that earlier. Q dot of t f is 0. Okay, so we had those four, but we also add q double dot t0 is 0, q double dot tf is 0. And so we have 6 conditions. So we start with by assuming a q, which is a 5th order polynomial, right? Because there are 6 constants in a 5th order polynomial, a1t plus a2t squared plus a3t cubed plus a4t4. I'm out of space. Plus a5t5. And the thing about this equation is that there are 6 constants. So you will solve for the 6 constants using the 6 conditions, and you'll get the trajectory you wanted. But there's a problem. If you look at if you look at the 5th, well, we looked at the second order, the second derivative of q, and we saw there's a discontinuity, so we went for a 5th order polynomial or 6 constants. But when you try to compute the the third derivative, okay, you know what the third derivative is called? Jerk. Jerk is discontinuous at t equals t0 and t equals tf. Okay, so what do we do? Well, we say the solution is add 2 more conditions. Add the condition that q triple dot t0 and q triple dot tf is 0. Okay, which means that if you add 8 conditions, you will have a 7th order polynomial. Okay, something like this: a0 plus a1t plus a2t squared plus a3t cubed a4t4 plus a5t5 plus a6t6 plus a7t7. And you go about doing a business of figuring out those constants based on now 8 conditions. There's 6 from uptail acceleration, but we added 2 for jerk. But there's going to be a problem, which is you'll find that the 7th, the fourth derivative will be discontinuous. And so you'll have to go for 9th and 10th and so on. So by the way, do you know what T4 is? It's snap, right? Snap. Okay, and then do you know what the 5th derivative is? They didn't teach you in dynamics. You know what the 5th derivative is? It's called crackle. You know what the 6th derivative is? It's pop. Okay, so what happens is pretty much you see that every time you choose a polynomial order, it's not good enough because the next derivative is going to be discontinuous. So if you add more constants, that will be satisfied, but then the next derivative and so on. So what people do is they really don't go to 10th and 12th order polynomials. They stop pretty much. When I do my work, I usually stop at acceleration levels, which means that I'll typically use a polynomial like this, a 5th order, and I'll be done. Sometimes people care about snap, so they will go for a 7th order polynomial, but that's about it. People will not go higher than that. So what I did was, it turns out that I wrote these equations, I inverted them, but you can actually invert them symbolically. What I mean by that is you can actually write the same equations I wrote down by using symbolic toolbox. So here is an example showing how to do this with the linear equation. So T0, TF, Q0, QF are my initial and final point. Here I actually sort of copy pasted A and B, as you can see, and then I can actually invert A matrix and then compute what X is. So when I run this on the right side, you should see the same equation. It's a bit doesn't really look kind of appealing there the way it's written, but trust me, that's the same equation I wrote down on paper. To give you an idea of what that curve would look like, I just put some dummy values for Q0, QF, T0, TF. I took those equations from that derivation, and then I just made a plot of Q, which is that same using A0, A1, which I found from that derivation, and then Q dot, which is the derivative, and made those plots. So here is you can see that Q is straight line, but the velocity starts at 1 and just remains 1. But then it all obviously starts, it should be 0 when you start with. I did not show that, but you jump from 0 to 1, and then here it will jump from 1 to 0, which is not good. So I did the same thing with cubic. Here I wrote the A matrix, which is that long expression I wrote on paper. Then I put B, and then I inverted A and got X. So if you invert this, it starts becoming nastier and nastier, right? So something like that. What I would do is, if I want to do this on a system, I would not really invert it here, like symbolically. I will just write this matrix in my code and then put in numeric values. So it will all be a 4x4 numeric matrix, and then invert it, because that inversion doesn't look that cluttered as it is over here. But then I took this same thing, A0, you can see here, this is copy pasted from here, and then put in some values for Q0, T0, TF, and just show you what the Q dot and Q double dot look like. So you can see Q is almost a straight line, except for that initial and final part where it tends to have a slope of 0. Velocity starts at 0, ends at 0, and then there's a hump. And then acceleration is a problem, right? It starts 0, but it goes to 5, and then goes all the way to -5, and then it has to go to 0. Okay, so you can take this code and you can, of course, use it for other things, like if you want to do a 7th order, 8th order, 9th order, you can do that.